Yeah, so before we discuss combination of lenses and silvering of lens, I would like to draw your attention to what power of a lens is. So once again, something that you are very familiar with after having completed your 10th. It has a formula 1 by f, and if your f is in meter, then your power is in diopter, and this is its SI unit, right? Diopter is the SI unit of power, optical power of a lens. Now, if you are using in centimeter, so what you will do, if you put 2 centimeter here, for example, so to get power in diopter, you have to convert that 2 centimeter to 2 meters, right? So 2 centimeter is 2 by 100 meter. So similarly, f centimeter would be f by 100 meter. So if you put f in centimeter, you will have to divide it by 100 and then make it meter. Only then this power will be in diopter. So I will say that the other formula is, so this is D, diopter is denoted by D. So it's 100 by f in centimeter D. So if you put focal length in meter, just take the 1 by the focal length. That's your diopter, power in diopters. If you have the focal length in centimeter, you will have to use this formula 100 by f and then put it in centimeter and get the power in diopter. What is power basically? It is the ability of a lens to converge the rays or diverge the rays depending upon its focal length, right? So I would say if a lens has a very high power, it will have a very small focal length. That means it will very powerfully converge all the lenses to a small, all the rays to a small focus. So for example, not to a small focus, to a focus which is at a very small distance. So for example, if a lens has a very small focal length, so it will converge all these parallel rays to this focal length. If another converging lens has a long focal length, so focus is quite far, it will converge them at a greater distance. So I will say this lens has a greater ability to converge because it can converge them to a smaller distance. So I will say this length has a greater amount of power or a greater power. So the ability is greater for this, that's why its focal length is less, and then if focal length is less, power will be more. So that's how you have to remember it. Same goes for the diverging lens also. So if you use a concave lens here, what is a diverging lens basically? A lens which has a negative focal length, right? That's your diverging lens. So a biconcave lens is an example of a diverging lens. So even a diverging lens has the if a diverging lens has a greater power, I will say it has a greater ability to diverge the rays, right? Because what that would mean is, if it has a small focal length, it will diverge all the rays such that these rays combine to this focal length. If it has a greater focal length, it will diverge them so that they get, the ability to the angle of divergence will be not that much, right? It will be less, because if it has a greater angle, the more greater angle it has, the more small its focal length will be, and the smaller angle it has, greater its focal length will be, right? That's how it is. That's the understanding. So if it is able to bend them at greater angles or diverge them at greater angles, it will have a greater power and a smaller focal length. If a lens diverges or converges the rays by a smaller angle, it will have a smaller power and a greater focal length. So that's the understanding of power of a lens. So let's take the combination of lenses now. So for example, I'll just derive a formula for combination of 2 lenses, and then I'll extend it to n lenses, because the same thing will happen. So for example, if I place this object here at a distance u from this combination, now you don't just have one lens, you have a combination of lenses. This combination will produce some image v, right? Now can I have a lens so that I can replace these two and I can just put that here and the object and the image position will not change, right? This lens, such a lens which I can replace with these two without causing a change, is called an equivalent lens, right? So the focal length of this lens will be called the equivalent focal length due to these two. So let's derive what that is. So first, for example, due to first lens, let's calculate what happens. So first lens will form some intermediate image at V1. So this U the rays will first fall on this lens. it will form some intermediate image at V1 and it has a focal length f1. That image will act as the object for the second lens, and then the second lens will form this final image V. So notice again here I am not putting any sign conventions. I am not putting a minus u here. I am not putting V. I am not giving any sign to V1. I am not giving any sign to V. No signs to focal length. Nothing. Because I am deriving a formula. While deriving a formula in optics, no sign conventions to be taken. Just derive it by the formula that you know. So 1 by V minus 1 by u is equal to 1 by f is something that is already derived and you know. Now while deriving another formula from this, while deriving another formula for this for a general case, don't put sign conventions here. When you solve a problem, right, when you solve a particular problem using this formula, you have to put signs. So I am not putting any sign here. So 1 by V1 is equal to 1 by u is equal to 1 by f. So this is your intermediate image. This is your object 1 by f1, and now this intermediate image acts like the object for the second lens, and this is your final image, and 1 by f2. So if you add these two, your intermediate object and image object which is acting as the image for the second lens, that intermediate object is cancelled. So you have a 1 by v is equal minus 1 by u is equal to 1 by f1 plus 1 by f2. So if you replace a lens, this is your f equivalent basically. If your lens has an f equivalent of f1 f2 by f1 plus f2, right? If you have two lenses here, this equivalent lens will have a focal length of f1 f2 by f1 plus f2 according to this equation. If you put that here, this 1 by v minus 1 by u is equal to 1 by f, you will get that. So that's how it goes. Like for example, if in general if you have n lenses in contact, here you just have 2. If you have n lenses in contact, this is the net formula. 1 by f like the equivalent focal length of all those lenses is sigma I is equal to 1 to n 1 by fi. That means 1 by f1 plus 1 by f2 plus 1 by f3 so on plus 1 by fn. Or else I can say the equivalent power of the lens is sigma pi I is equal to 1 to n. Nothing different. 1 by f equivalent is power, because power is 1 by f, right? So 1 by f equivalent is power equivalent power of the lens of the lens that will replace this combination, and 1 by fi will be pi basically, right? Pi will be equal to 1 by fi, where I runs from 1 to n, and you will cover all lenses when I runs from 1 to n. So this is the formula. So in fact, the equiconvex lens that we saw when we derived what is the formula? Lens maker's formula. In that you had equivalence, equiconvex lens, right? So this side you had mu1, this side you had mu2, and this side you had mu1 again. For example, if you have mu3 here, how will you solve it? Like in that formula there was no space for mu3. You just had mu2 by mu1 minus 1 into 1 by r1 minus 1 by r2. That was the formula. You didn't have any mu3. For such problems, what you do? You divide this lens into two halves. This is a plano-concave convex lens. This is another plano-convex lens. This lens has its surrounding medium as mu1. This lens has its surrounding medium as mu3. Calculate the focal length of this lens using that formula, treating it as a plano-convex lens, right? For this lens, your R2 is infinity, right? For this lens, your R1 is infinity. So now divide it into two lenses and treat them as plano-concave convex lenses and calculate their focal lengths, and then you add bring them close, and then you will say the net focal length is 1 by, if the focal length of this, if the focal length that you got for this was f1 and the focal length that you got for this was f2, using that formula, 1 by f equivalent will be 1 by f1 plus 1 by f2. That's how you solve it when you have such cases. And when you have mu1 itself, even then you can solve it and verify that formula. You can solve it using this method. Take the equivalent focal length and verify if that formula is right. So there was a technique that I wanted to give you. No time to discuss problems as such, but this is the technique. Now let's come to silvering of lenses. So what do you mean by silvering of lenses? You have a lens which was supposed to show a refraction, but the moment the light rays entered, one face of the lens was silvered. Right? What does it mean? This inner face, like not the dashed one, the opposite one, right? That part is silvered, so that part acts like a mirror. So what happens is your right rays enter, they hit this surface and they reflect instead of refracting through the lens, right? So for such cases, how do you derive the formula? There is just one formula that you have to remember for all silvering cases. So whether your biconvex lens is silvered, or whether your plano-convex lens is silvered, or whether your plano-convex lens with its plane surface is silvered. So remember, this and this will make a difference. If the convex side is silvered, sorry, the concave side, right? This inner side. So if this is dashed, that means this inner side is silvered, and the inner side is the concave side. So if the concave side is silvered, and the same lens, for the same lens, if the plane side is silvered, it will make a difference. Like both of them will make a difference. So what you have to understand is, or else even if you have a concave lens with its one of the one of the convex faces silvered. So remember, if this is dashed, this is your convex, this face that I am talking about, it is this face. So this opposite face, which is your convex face, that is silvered basically if I put dashed like this. So this is the formula that you have to remember. What is this formula? First of all, remember, if a lens is silvered, it will act like a mirror. How? Your light rays will come, they'll get reflected, they'll get refracted through the lens again. So basically, it acts like a mirror. It doesn't act like a lens anymore, because the object, the rays don't go on the other side at all. It acts like a mirror. That's why the equivalent power of the mirror. So if I can replace this lens with a mirror, so remember this concept of power of a lens, it is the same for a mirror also. Like power of a lens or mirror, I'll have the same formula and the same concept basically. So if I replace this lens with a mirror, what will its power be? It will be P equivalent, right? And then that is equal to 2 into power of lens. So remember, forget about the mirror now, forget about the mirror, forget about the silvering. Why should I have two times the power of lens? Because the light rays, how it goes is, let's take this lens and try to understand this formula, just this one. So you have a biconvex lens, this side is silvered. What happens is, first your light rays go, they get refracted in the lens, so they get refracted, they hit the mirror, they get reflected, and while coming out, they get refracted again. So don't mind the diagram here. So they get refracted once, and then once again when they come out, they get refracted. So that means they get refracted twice. That's how this combination is basically a lens plus a mirror, where your mirror is like a concave mirror, right? Your mirror is a concave mirror. So that's why you have 2 into power of lens and a power of a mirror. So what mirror you should use? The side which is silvered, that is your mirror basically in this formula. So in this case, your concave side is silvered. So the power of the mirror will be negative. Why? Because a concave mirror has a negative focal length, so it will have a negative power. So you will put a negative P here for if this is the case. For this case, your convex side is silvered. That means it acts like a convex mirror. So for such case, your P mirror will be positive, because power for a convex mirror is positive. So, and what is the P of lens here? Forget the mirror, like forget the silvered part, just take the lens, right? So remember this, the focal length for this lens and the focal length for this lens are different. So for example, if your right rays are going like this, how will you use it? This is mu1, mu2, mu1. The focal length of this lens is 1 by f is equals to mu2 by mu1 into 1 by r, where1 by r1, where r1 is the radius of curvature of this first surface, that's infinity, minus 1 by r2, which is your negative. So you have a minus 1 by r2 here. And if you have this surface, if your light is incident on this surface, 1 by f is mu2 by mu1, and if this side has a radius r1, the other side has r1, the other side is infinity, so you'll have a 1 by minus 1 by infinity. That will be the focal length for this. So remember, again, if your r1 is equal to r2, like if this radius and these radii are same, they'll have the same focal length, then it will not matter. But whatever it is, use the appropriate, like forget the silvered part, incident the rays, and use this formula, calculate the focal length of the lens. 1 by focal length of the lens is the power of the lens, multiply that to 2 and put it here, right? 2 into power of lens. And now forget about the lens, look only the mirror. Look the mirror that is silvered. So here this will act like a concave mirror, this will act like a concave mirror, this will act like a plane mirror. For a plane mirror, radius is infinity and power is 0, because radius is infinity, so focal length will be, for every mirror r is equal to 2f is valid. For lens it is not always valid. So if your radius is infinity, focal length also will be infinity. If focal length is infinity, power is 0. So for a plane mirror, radius is infinity, focal length, radius infinity, focal length infinity, and power will be 0. So you'll put a p is equal to 0 for this case. This case, your convex side is silvered, so you'll put a positive power here because the convex side has positive power. So look in the diagram what your mirror is and put the power for that mirror. After that, forget the mirror, calculate the power, focal length of the lens, 1 by focal length, calculate the power of the lens, multiply that to 2, and this is the power of your equivalent mirror, right? And then 1 by power of the mirror is basically your focal length. So in fact, silvering of the lens can help you find out, this formula can help you find out, if I have a mirror, what will its power be and what will its focal length be, right? So now I can replace this, I can put this mirror, I know its focal length, and then for a mirror I know, okay, 1 by V plus 1 by U is equal to 1 by F. So if my object is at U, I can find out what V will be due to this combination, because I can replace this and I can put this mirror for which the formula I already know, and I already know its focal length from this formula. So that's how it is for silvering of lens. This was the concept. With this we are done with lenses and mirrors completely. We'll now proceed with the concept of critical angle and total internal reflection. So let's go.